Okay, hey everyone, and thank you for joining us to this, I believe, 8th OceaniX webinar meeting. Today we are extremely glad to welcome Jakob Runge, who is the head of the Climate Informatics Group at the German Aerospace Center. He's also a guest professor at TU Berlin, and he's going to talk to us today about causal inference and causal discovery, mainly in climate, I believe, and science. So as usual, we'll have a 45 minutes presentation followed by some discussion and questions. And you can also write your questions in the chat during Jakob's presentation. That's all for me. So Jakob, you can take the floor and start with your talk. Thank you.
Yes, thanks very much for the kind introduction and invitation to present here. So I come from physics and then wandered into network theory and causal inference pretty early on in my PhD, and have now been adapting this to climate data for the past decade or so. And I found it quite useful, and hope that also the kind of framework that I present here may be useful to your research. So I made the talk quite tutorial-like, pedagogically, kind of, and less so on specific methods to really get you a grip on what the concepts are, and then you can look in references that I will mention on the way to find out particular methods in talks. All right. So I start kind of historically with a little quote on the relation between causality and statistics. And this comes from Carl Pearson, who is an eminent, maybe signal processor, statistician, because he invented the Pearson correlation coefficient. And he was kind of an antagonist to causal inference people at the time, if you had that crowd back then, as you can see from this very elaborate gentleman talk that you can see here, and that I will not try to read out. So he was an opponent of the category of cause, and basically founded this mantra that correlation is not causation, and instead there was a steep abyss between statistics and formulations of causality based on data. So there was, of course, the other sciences, but there was never the mention of the word causation when you just use data analysis. So that was for some decades, or maybe even half a century. And in the past 2 or 3 decades, the work of Pearl and Spiritus, Gleamer, and Chaix, those people below here, has made causal inference kind of an important subfield in many parts of science. And what maybe their basic point is that, yes, correlation is not causation, not generally at least, but the field of causal inference is really about identifying assumptions and methods that enable to learn causal relations from observational data. So the important word here is assumptions, because that is what grounds the data analysis tools in a mathematical foundation that give rise to causal interpretations. This book of Why here is quite a nice popular science read with lots of examples and anecdotes. And of course, there's more literature that I show at the end also that introduce. So today I will divide this into 2 subtopics. One is observational causal inference, kind of the overarching part of the framework, and then more specifically causal discovery, which goes into how to discover structure from data and not just how to work with causal structure. And yeah, some brief mention of the state of the art and application examples that maybe inspire you for your work. Okay, so to put it in short words here, what causal inference is about, it's a mathematical language for causal notions such as cause and effect. That is really the achievement of the people mentioned before, Pearl and so on, to ground causal language in a mathematical language. And it provides then methods and assumptions for answering causal questions from observational data. So this is what his book mainly is about. And another part is causal discovery, which is about learning causal graphs from data. So maybe the fundamental question of causal inference, and a question occurring everywhere in science, is, given just two variables maybe, how we can determine whether and how X causes Y. And this question has usually been answered by experimentation. So we are in remote sensing audience here, so that's not quite what this audience is used to. But in many fields, and for the past centuries, since Galileo Galilei, experimentation has been the way forward to do this. And you would then manipulate X and keep all other conditions the same in a well-controlled experiment. And then if this results in a change of Y, then you would say that X causes Y, quite intuitively. And in the notions developed here, this would be referred to as an intervention. By the way, there's a little kid in the back. I hope it doesn't disturb too much. One example is the lawn with a sprinkler, taken from Pearl's book also. So when you turn the sprinkler on, then the lawn will get wet. But if you make the lawn wet, on the other hand, this does not turn the sprinkler on. So if you do these two experiments, then you can readily infer what causes what here, even without knowing those two concepts. On the other hand, if you look at observational data of the lawn being wet and the sprinkler being turned on, then from the correlation or so, you will not be able to infer such a statement. You had to intervene here. When we are now in this field, where in remote sensing or in climate sciences more generally and many other fields, there's two important challenges, namely the one that experimentation is just not possible on a large scale in climate. Arguably ethically, on a technical side, of course, expensive and so on. So when you want to answer questions such as whether and how much aerosols influence clouds, so here we know that they do, but we don't know how strong this effect is. And as you know, this is an important factor in climate change models, and therefore in climate change predictions. So aerosols and clouds are both influenced by a large number of environmental factors, from humidity and temperature and so on. And these factors now make it impossible to just learn from the data the effect of aerosols on clouds. If you were to intervene, then this would be possible, because then you would just set aerosols, for example, to some level and then measure how this affects clouds. But this is not possible for the above mentioned reasons. And therefore you have a confounding relationship here. Another challenge is that often the ground truth is not known. So we do know ground truth, like the Navier-Stokes equations, on a very microscopic level, but our questions of interest are often among macroscopic variables, like sea ice extent, how that influences some other variable, or El Nino, or more aggregate quantities, where this is just, or in the biogeochemical cycles or so, where we have dynamics that are not that well understood. Now, an approach to this is based on this physical knowledge that we have to use our our climate models, which enable experiments without harming anyone. And in these, you can fix parameters, you can analyze the effect of, for example, fixing sea surface temperature and measuring its effect on atmospheric dynamics. But of course, the extent to which this results transfers to the real world is limited by the realism of the models. And there's a lot to do about using different climate models in an optimal way to predict climate projections. And the other approach is that of observational causal inference, which is the topic here. And that would make use of the ample availability of data that we have due to satellites, due to measurement stations, and from many other sources. So in the following, to introduce this topic, I will formalize the idea of an underlying structural causal model, which forms the basis of this framework. then define what hypothetical interventions are and establish identifiability criteria, which tell you whether and how causal effects can be estimated from data alone without intervening. So that's exactly the link that is the goal of causal inference, to measure causal effects, to use assumptions to measure causal effects, estimate them from data alone. So I will stay on a conceptual level here. The intuition behind a structural causal model is that it specifies the functional causal relationships between the set of random variables. So in the previous example, the aerosol variable, for example, the value of that would be dictated by a function of the environmental factors. And by eta here, we have some complex processes that are only influencing the aerosols here. So this is the assumption that the eta terms are independent among each other. Therefore, you would have to extend your structural causal model in such a way that in the end, whatever remains as processes causing one of the variables is independent of the others. Clouds are here a function of aerosols and these factors in this graph, and the environmental factors may only also cause each other. So the claims here is that this structural causal model specifies the direct causes of each variable. These are exactly the arguments in the function on the right-hand side that appear in a non-trivial way, of course, to exclude mathematical objections here. And those functions fi are considered as independent mechanisms by which nature determines the values of each variable based on the values of these direct causes plus random fluctuations. So they have a interpretation as really being independent of each other, so that you are able to intervene in one variable without changing the others. And that I will explain now. These interventions in this mathematical objects, and that's just a formalization that Perl uses to ground causal reasoning in this mathematical language. So these interventions, they now model this notion of experimental manipulating X while keeping all other conditions the same. So I show the same equations and the graph again. Before, when we consider the observational data, we would have this being the process that generates the data. So our observational distribution would come from this process. And if we then would intervene, that is represented by the do operator in Perl's language, then this intervention would be structured as follows. Namely, we would replace the equation of aerosols here, kind of delete whatever functional relation we're determining aerosols before, and set it to some aerosol concentration. So this happens when you intervene, experiment, and set the variable to some level. And in the graph, this would be, if you delete kind of the equation, if you knock it out, this would imply that you also knock out how environmental factors cause aerosols. So the general formalism is now to define notions of causal effect, namely when this distribution of y, how y changes under the intervention of x, can be estimated from the observational distribution. And in general, this is an important notion. The introduction of this do operator here is not the same as the conditioning on the right-hand side here. So P of y do x equal small x is typically not the same as the probability of y given an observed x, which is a property of the observational distribution. So based on the causal graph, the formalism allows to decide whether the effect, this do quantity here, can be identified from observational data. So whether you can find a formula of the observational data. And if so, then this is an expression that we can use to estimate it. So the following, I will iterate through this idea through some examples. So for example, here, if we have this as an underlying causal graph, where The structural causal model would be something like y is c times x plus noise and plus b times z. And if that is the underlying causal graph and you want to measure the effect of x on y, you would just fit a model of y on x. And in this case, this might just be a linear model. Because if you assume that the relationships are linear, if not, you would fit a more expressive model class to this relationship here. But what about the case that you have an observed confounder here? Namely, if z also causes x, then just fitting a model of y on x is, so as before, would not be enough, because then you would ignore that both variables are driven by z. And to control for z, you would just add z to the model. So you would fit a function of y on x and z. And if you make a linear assumption again, then this would be a linear regression model, y with a beta coefficient times x plus other beta coefficients for one or more z variables. And then this beta coefficient, if you use this regression model with this variable z here, is the same as the causal coefficient. And this exactly means identification. Because when you intervene in x and change it by some value and measure the effect on y, you would get a c times the changed value effect when you intervene. And the same you can obtain from the observational data by this multivariate regression model in this case, and more generally by fitting a function that is expressive if there's underlying nonlinearities. So the whole theory is non-parametric. What about this graph? Now we have a mediation example, x causes z and z causes y. And now you would not condition on z because that would block any path. And basically, if you fit a function of y on z and x, you only get a non-zero coefficient for the z dependent variable, but not for x. So to measure these indirect effects here, you would fit again a model of y just on x. Another case, what if we have an unobserved variable L? So I mentioned before that the structural causal model is really the underlying concept, and some of the variables may not be observed, but maybe you are nevertheless able to draw a graph that that gives you the relationships among the variables, and that the fact that it's unobserved just means that you would make it like not be able to condition on it, not be able to put it in a model. And because of that, because here you cannot fit a function y of y on L and x, it means that the effect cannot be identified for this graph. What about this, the common effects case? X and y both cause another variable s. And also here, you should not control for common effects of x and y because this introduces a bias to the model. So again, you would not get the correct causal effect here, but you get something due to the common effect of s. And as a side mark here, as a side remark, sometimes this is unavoidable. For example, if your whole data set contains missing values, and the reason why values are missing is not just random, but it's caused by the factors x or y. Mostly the problem is y here. That introduces a bias, and this is a form of selection bias. So in a more complicated case here, where we have a number of variables and some of them are unobserved, we need some criterion to choose what other variables to put in our model next to x. And this is given by, as one sufficient criterion, by the Backdraw criterion. And the criterion tells you that a z, which is called an adjustment set, satisfies this criterion for identifying the causal effect of x on y if, firstly, z blocks all non-causal paths between x and y. So here this would be achieved by including Z3 in the model, but it would also be achieved by including Z1 or Z2 in the model. Both of these block paths. And the way to read off when a path is open or blocked, which is by deseparation, as in usual causal or in usual Bayesian networks, is the only thing you need to really remember is that whenever there's a tail at a node and you walk through a motif that contains a tail and that node is not conditioned on, you can walk through it. If it's conditioned on, then it's blocked. So here, this is a blocked motif. This is open, but this is blocked. And this was also blocked. Therefore, these sets block all non-causal paths. The second condition is that no element in Z is a descendant of Y or mediators. And this is excluding this bias that I mentioned before. So you neither should include this variable here on the right, descendants of Y, or the one that is a descendant of a potential mediator. If you go by these rules, if you find some subset of the other variables Z that fulfills these, then this theorem tells you that this set satisfies the vector criterion, and then you can identify the causal effect. And that means that you can estimate that you can that you have such a functional relation of Y given do X, which is the quantity we cannot get at because we cannot experiment with a system. But this is exactly the same as this quantity on the right, where you marginalize about Z and consider the conditional density of Y given X and Z. And in a linear assumption, the expectation value of this quantity there would then yield to this beta coefficient again. So you fit a model of Y on X with and on the confounders. And then the causal effect is given by this beta coefficient in front of X. So that's a nice way to do causal inference. As a little outlook more in this topic, if you have unobserved confounders and mediation here, and that Z is not caused by L, you can not apply this vector criterion because there's no set that blocks all non-causal paths because L is unobserved. But there's the frontal criterion, and you can read more about this in Perl, but just suffice to say that there's more than the vector criterion. There's, in fact, a full calculus, the do calculus, that is complete, which means that for any graph, it will tell you whether or not there is some way to estimate the effect. And this might not always be by this simple formula here, but by more complex formulas. And if that is not possible for the graph, then there's results that will tell you for a given graph. So moving forward to causal discovery. So in the previous section, we had a knowledge of a causal graph, qualitative knowledge. And from that, we could then estimate causal effects. But what if we don't have access to, we have not enough expert knowledge on the causal graph, we have maybe limited or no knowledge about it. So how can we learn a causal graph from data? And this is exactly the topic of causal discovery. And I will do this by some intuitive riddle, which works you through the main approach to causal discovery in terms of the work put forward by Spiritus, Klima, and Chaix, the three guys in the second slide. And this goes as follows. So it makes use of two important assumptions, and I will try to convince you that these are reasonable. So the exercise starts as follows. So you are given two variables, X and Y, and you have data. And this data looks as you see here in the scatter plot. And doing any statistical analysis, you would say that they are correlated, mutual information, anything is non-zero here. With a high confidence, you can make that statement. Now, that being a statistical dependency, and us wanting to know about causal relations, what causal relations are consistent with this observation here? Well, we know that X could cause Y. This could be a causal relation that would produce such data. But the same would hold if Y causes X. You would get the same kind of data, or you could get in principle the same kind of data. And lastly, if there's a confounder between X and Y, you might also get the same kind of data. So we're kind of left with these possibilities. And now if you say that, or if you are happy to accept that these are three potential options, are all ways by which this data can have been generated, then you make the causal Markov condition, namely that statistical dependence implies that there must be some kind of causal connectedness, and this might be indirect, this might be due to a confounder, but that there is an underlying structural causal model with an associated causal graph such that these two variables are connected in the graph. Moving forward, what if we have access to more data? This is always beneficial. And what if now, again, we have a large sample and three variables, 3 dimensions, is a 3-dimensional scatter plot. And now we measure not just dependence. So we would measure that Z and Y and X and Z are dependent. If you kind of look at this from the left and the front. But we can also measure conditional independence. And this is defined by this P of X, Y given X, given Z, factorizing into P of X given Z times P of Y given Z for all X, Y, Z. And is denoted by this X orthogonal Y given Z. So suppose we are able to measure that with high confidence, and our Bayesian or our frequentist test tells us that these are independent. So now, what from this knowledge about the data, which high confidence of this knowledge, what do we again infer or conclude back in regarding the causal relations in the graph? Because this above is really about causal relations and not about statistical relations. So the question is, does this link here exist? Because we just found that it's X and Y are independent given Z. And if you're now happy to remove this link because you say, well, there's no statistical dependence, so how can there be some causal connection that is not due to Z? If you are happy to accept that actually there cannot be a causal relation between those two direct one, then what you made is the faithfulness assumption. Namely that statistical independence implies that there's no causal connectedness. So this is basically the other implication of the causal Markov condition, the other direction. And if you make this assumption, you delete the link from the graph, and now are left with this funny circles here, and they are just representing that there could be the confounder Z, but it could also be that there's a chain in one direction or in the other direction. We cannot distinguish either of these three cases for this case. We can only distinguish that X and Y cannot both be a cause of Z. That is not consistent with this conditional independence. There would be actually a conditional dependence. So these three possible graphs form a Markov equivalence class and cannot be distinguished from this one data set with this statement of X, Y independent given Z. So let's bring more data, more variables. And suppose that the additional variables now have the following relations with the other variables. Namely, V and W are actually independent, unconditionally independent. And then for all other pairs, it holds that they are independent given Z. So that holds for XY, XV, XW, YW, and so on. So now, because of these independencies and the faithfulness assumption, you would only draw these two additional links. And now, again, we are in the phase of reasoning. What are possible relations? Is it the same as above, that we can have Z being a confounder or one direction or the other? Well, if you now take the the conditional independencies, or in particular the unconditional independence of V and W as evidence, and look at this graph now, then this is not consistent, because if this was the correct causal model and we assume the faithfulness relation or the contraposition, namely if there is a connectedness, then there has to be a dependence. If you take the contraposition of the faithfulness assumption, then there must be a dependence between V and W if this is the correct causal model. And since this is not the case, we can exclude that. We can also exclude the other direction, and we can exclude that being a common driver for the same reason. So actually, among the potential 4 options, only this one is consistent. Both must be a cause of Z. There must be, more importantly, an arrowhead at Z from both of V and W. So to make this conclusion now, we assume that there's no unobserved variables for this slide now. But let's look now at the implications of knowing these relations on the lower part of the graph for the upper part. Because we had the Markov equivalence above, but now this changes. So for example, this, which was a member before, can this still be a member of the Markov equivalence class? Well, if we look at the evidence again, then W and Y are independent given Z. But if this is the case, then this rule of D-separation tells us that conditional on Z, there must be a dependence. It's this collider bias where you would get a dependence. And also unconditionally, W and Y would be independent for this graph, while they are dependent. So this is inconsistent. The same for the other side, and the same for both sides causing Z. So what remains is only this motive, this possible orientation of the links in the above part. And therefore, we can conclude just from looking at these few conditional independencies that this is the only graph that is consistent with these independencies, and that was derived from the Markov assumption, faithfulness assumption, and the assumption that no unobserved variables exist. And finally, extend that to the case that we allow for arbitrary latent confounders. And now look again at the graph. If you explicitly draw such a confounder here into the graph and assume that it has this functional relation with X and Z, and look again at the conditional independencies, then if this was the true underlying graph, we would not observe a dependence between V and X. So this is a little more complicated. From X, you can walk through L, but you cannot walk through Z to V. So this is blocked. And again, by our assumption, we would then have no dependence between X and V. But in the graph, in the observations, we found that they are dependent. And this rules out the possibility that there can be such an L in this direction. On the other hand, there can be an L on the way from Z to X, and also not in the other direction by the same reasoning as before. Hence, we learned that Z to X is a causal link. It might be indirect, but it can be interpreted as a causal link. What about the lower part? Is this consistent with the observations? No, because then V and W would be dependent by this relation here. But on the other hand, this we cannot exclude. If this is true, then V and W would be independent, and they would be dependent given Z. And all the other relations also hold, as you can convince yourself. Hence, we cannot really exclude the possibility that there is a confounder between V and Z. That's why we leave this this circle mark here to indicate that in the Markov equivalence class, there's also the possibility that there is a link here, like an arrowhead or a tail. So in both cases, we know that Z is not a cause of V and W, but yeah, we don't know whether V is a cause of Z, and the same for W. So we are left with this graph, which is already quite informative, at least for the relation from Z to X. Causal inference now. is based on using such assumptions and observations in the data, condition independence for one case. And many more, for example, time order. So to recall these assumptions, because they are the main part here again, one was that we assume that there's an underlying structural causal model. And this implies the causal Markov condition that deseparation in the graph implies conditional independence, or dependence implies a connectedness. And the faithfulness assumption, which was the other direction. And we, in one part of this riddle, had used a causal sufficiency assumption, but this is quite arguably unrealistic in many cases, and can also be dropped if you are not willing to make this assumption. Then the algorithm or the implications we showed work in some cases, but often you are left with a large Markov equivalence class, so you cannot say so much about causal relations. But this very much depends on the data and what you learn. So algorithms that automatically do that, what we've done by hand here now, are the SGS algorithm, which is kind of inefficient, and the state of the art would be rather the PC algorithm, which is much more efficient in terms of complexity, but uses causal sufficiency. And the FCI algorithm is similar, but it does not require the assumption of sufficiency. So the FCI algorithm would give you the graph that we did by hand now, just based on the knowledge. So in time series, we have the advantage of more expert knowledge, more side knowledge, because for once, causes can only go in the future. You cannot cause the past. And hence, if you have a link from a lagged variable here, then that always needs to have an arrowhead at the future part of this link. And the representation here is slightly changed from before. Before there was one node per variable, and now for representing the time resolved relationships, we would include each variable at different instances of time. And now, assuming stationarity, whenever you have a link for this pair, you would also have a link for this pair in the past. So in this way, you can represent arbitrary relations among variables at different time lags. And they can also be contemporaneous relations, of course. This might be more a useful notation. You can argue that there's no instantaneous causation if the time resolution of your process, of your data, is high enough because of the finiteness of the speed of light. But of course, it's kind of practical to be able to also model such relationships. So when you take this time series graph and contrast it with another representation, namely the summary graph, then for this acyclic time series graph, we would still observe a cyclic summary graph. And this is not a nice object for causal inference. Having cycles is not in the Bayesian framework allowed, and also puts you into trouble in defining what a structural causal model could be that gives rise to such relationships. So in essence, I want to say that for time-resolved processes, often what appeared as cycles in the untime resolved data resolves. So what my work has mainly focused on is on the statistical issues and high dimensionality and conceptual improvements of the PC algorithm for the time series case. And this would be the PCMCI and PCMCI plus algorithm, which addresses these challenges. And another recent work of last year was the LPCMCI algorithm, which allows for hidden confounders. So this is basically the end of my overview over these two concepts. And now I will go a little bit, just a few more minutes about the state of the art and then some applications. So I have a perspective paper together with many people from the causal inference community and from climate science where we put together the state of the art in causal discovery and some challenges, and where you can find a lot of references to further work. So there you get an intuition of how Granger causality fits into this framework, which I don't want to cover now. You get also some more explanation of these network learning algorithms, which essentially do what we've done in the riddle, but automated. And this is more an illustration here. But one particular issue that I want to mention now for briefly is we've seen that there's still this problem of Markov equivalence. So even here, because X and Y in this case don't have any colliders going in basically and happen at the same time, have a relationship at the same time, we are not able to distinguish whether X causes Y or Y causes X here, even assuming sufficiency. So this is the result that you get from just assuming Markov faithfulness and sufficiency. And when you want to go beyond, then the theory of structural causal models, of restricted structural causal models, comes into play. And this is work mainly by Jonas Peters, Bernhard Jakob, and Dominik Jansing, or at least they have written a textbook on this that nicely summarizes this and have done a lot of work on this. And that addresses especially this Markov equivalent case. And what they use is not magic, but additional assumptions about the data. And in particular, if you have non-Gaussianity in your variables, then they have a result and a method how to identify whether X causes Y or Y causes X. And just visually, you fit a model in both directions and then look at the residuals and how they relate to the potential cause. And if there's an independence observed, then you find the correct direction, namely here that Y causes X. On the other hand, just to visualize what happens when you have Gaussian data and fit a model in both directions, then the residuals will be independent in both cases. So you cannot identify it unambiguously here. There's this theorem that tells you that just for Gaussians in a linear model, you have this property. So any non-Gaussianity helps. I will not mention state space models. They assume an underlying chaotic system and a deterministic system. So they are not really made for the stochastic case, even though they would still be applicable. And it's an interesting work to relate these concepts with each other. And I've done a little work in this direction if you want to read in the papers of mine. So coming to the applications, you may look at the challenges here in the paper at this figure more, and I want to mention a few application examples. And they cover maybe the topic of testing causal hypothesis as being most imminent as a useful application. Then you can use statistical prediction schemes with this, and you can evaluate climate models. And that's what I want to show briefly. So just maybe skipping over this example. One work that is some years ago where I used this causal discovery approach to identify the network of pressure components, which I identified by dimension reduction beforehand. So I decomposed the whole sea level pressure field into 60 components and then inferred the network among these. And that then allows to, for example, also look at indirect paths. So for example, here, the East Pacific causes the monsoon region by different pathways. And one of them that is most strongly, as I find in this work, is through the Indonesian archipelago. So this kind of information, not just about whether or not a link exists, but also how strong they are, can be done with causal discovery and inference. Coming to the topic of prediction, we often face the challenge, as is identified in this work by my colleague Marlene Kretschmer, that you have a variable field and you have one target quantity, here, for example, the stratospheric polar vortex, and you want to identify optimal set of predictors. And in this work, we used kind of a supervised dimension reduction with the stratospheric polar vortex as a target variable, to identify regions with high relationship with the target variable, and those would be then those clusters or so. And then you run causal discovery based on these aggregate regions with the target variable and identify a subset of causal predictors from this. And this then builds a more parsimonious prediction model of the stratospheric polar vortex at some lead time as a function of these causal predictors. And these regions can then also be looked at and identified whether they make sense or not. So it allows to directly interpret them better than maybe you could do with a deep learning model, where you would stick to sensitivity analysis, and that is not really what giving rise to a causal interpretation. And lastly, the topic of causal model evaluation, which is work together with Per Novak of last year. And here, this tries to provide a complementary approach to model evaluation as it's done now. So we have observations of some variable, in this case it's GPP, for example, and we have climate models that produce modeled GPP, and you can look at their absolute values, for example, and run a model evaluation there, like whether the model well represents the values or the GPP at a particular point. Now, what about this alternative? Namely, you define some variables that are then really coming from what you are interested in and what process you want to analyze. You define variables based on your data, maybe some spatial averages, but not necessarily. And then you run causal discovery on the observational data. And you get some observed causal network and maybe also some link weights here, some strength of links. And now you do the same inside each of the models. And you may get different causal graphs and a spread. And now you can compare whether the observed causal network has much to do with any of the models. And this would then be complementary because it measures how well the models represent the causal dependencies in the data. And therefore, we call this causal model evaluation. Of course, in how far this is under the assumption of sufficiency or not is then up to your choices of reconstructing the causal network. So we did this in this work, again, on Varimax components. We made some tests and found that the same climate models give rise to similar networks, so they cluster, which is comforting because that means it's a robust metric. Then you can rank them, how well they, by the F1 score, represent the observational data, and use these to do other things. Now, in summary, coming to an end, causal inference, and I hope to have made that point clear here, is about answering causal questions from empirical data. We discussed two settings, one where the causal graph is assumed known and you wish to estimate causal effects. So here you use really the expert knowledge that is often available, the qualitative expert knowledge. The second one is when you don't know the graph. You then could do causal discovery and then, of course, still estimate causal effects, which then have to take care of the Markov equivalence. These methods here are all based on assumptions, and the one being that we assume that there's an underlying structural causal model or the Markov condition. If we do causal discovery, we require things as the faithfulness assumption. Maybe if we can and we know that in this case our data set is kind of complete, we may assume causal sufficiency. And we may make additional assumptions on dependency types like linearity and so on, and that will then give rise to which particular model we fit in the causal effects part, and which, for example, independence tests or which other models we use for learning the graph. Time series data gives us time order and potentially stationarity. If you want to assume that, it helps. And these assumptions can sometimes be tested and sometimes not be tested from the same data. And therefore, causal conclusions would require to state these assumptions and explain reasons for believing them, and then indicate, for example, also how conclusions are altered for different assumptions. Therefore, you would be very transparent about how you gained your causal conclusions from just a pure data analysis, by stating these assumptions and arguing for them. And with this, I would like to close and leave you with these references. Thanks a lot.
Thank you, Jakob, for this very interesting talk, very informative. And we have the time now, yes, for some questions. So anybody in the audience?
Yes, I can start.
Go ahead, Carlos.
Okay, thank you very much. I understood that causal discovery is, can be confusing because there are a lot of possible links between the processes. I mean, from my knowledge, causal relationships need a time dimension in the processes that you are studying. So I didn't understand why you differentiated between processes at the beginning of your talk and time processes later, because how do you define causal relationships without a time dimension?
Yeah, very good question. Because as a physicist, I also would think in terms of all the ODEs and everything being dynamical. But this whole theory is really not necessary. I mean, this time assumption is not necessary. So all that we discussed here in this riddle didn't make any reference to time. Time would be helpful if you knew that V is time lagged or Z is time lagged. You could make more conclusions and draw more conclusions here, but we haven't used the concept of time. So this would apply, for example, to things like, I don't know, taxation and GDP or unemployment rate. These are typical cases where such methods are applied, and you don't need to have observations coming from time. They can come from different patients, for example, or different subjects or countries or so. So I really hope that this riddle here explains or gave you an intuition that, well, Z must cause X, otherwise this conditional independencies cannot be observed.
Yeah, I see with the example, with the examples you are giving, I understood that you can observe. I mean, it's difficult for me because I was in the framework of binary causality, and so with a time arrow, and in this case, for example, in this causal graph that you draw, no, in the slide we were in the slide 17. We observed at a given moment, you said that you cannot decide if there are some arrows from X to Z to Y or from Y to Z to X. And that was, you were in the case of no time direction, because if you have that time, you can always condition by the past of X, Z, and Y, and then you can use binary causality to decide whether X causes Z or Z causes X, right?
Yeah, maybe I discussed this again, because here in the paper we discussed Granger causality. So Granger causality is you fit a model of Y on its own past and include X in one model and exclude it in another, and then measure whether there's a significant change in the residual variance or some other method. It doesn't matter. And that is basically, in information theoretic terms, the following. You measure whether there's any information in the past of X about Y that is not contained in the past of Y. So this is what transfer entropy, for example, measures, a generalization of Granger causality. But what transfer entropy measures, it's an information theoretic quantity, and it's nothing else as it's an independence test in the end. So when X is independent of Y at time t, given the past of Y, then there's no causal relation. And if they are dependent, then you know that there is some path from X at the lag to Y. But if you extend Granger causality, including other Zs, you can exclude paths through the other Zs. But what you cannot exclude is a contemporaneous relation. So for example, that's why I show this in the paper. Here, y at time t minus 1 causes z at time t, and that causes w at time t. And Granger causality would be non-zero from y at t minus 1 to w, even though there's no, even though you put that in the model. And that is because Granger causality cannot deal with contemporaneous relations.
Yeah. Newly, I'm maybe I come from physics. So how do you? I mean, how can you define instantaneous causal relationships? Because for me,
Yeah, well,
if you,
yeah, I know. I would.
physics,
I think. What if you have monthly data and the atmosphere influences itself or different regions at a daily time scale? So what you end up is, if you only have monthly data or you have daily data, your aggregation level of your time series is just not high enough. Then
so
you
it's a
get
problem of time sampling.
Yeah, I mean, time subsampling is even a different game because there you skip some variables, and that is kind of having latent confounders inside the time domain. That is discussed also in the perspective here. But this is about, yeah, not, well, time aggregation maybe.
Okay, thank you very much. I let the others ask some questions.
Okay, so I think I do have a question. So regarding your data, do you use that data, and specifically how important is the variables you consider in building your causality graphs? I mean, for example, if you take climate data, do you take data on a grid, or do you do dimensions reduction on some specific variables such as pressure, for example? And how do this dimensionality reduction affects the results of your?
Yeah, very good question. And it the causal inference, people would maybe tell you, well, you have the hypothesis on the variables. You have an hypothesis of which variables you are interested in. We cannot tell you how to also do dimension reduction, because that is kind of a separate problem. So the input to causal methods is kind of always the nodes of the graph, and then you learn the edges and the orientations.
Yeah, but for example, if you have, if you are interested in the wind speed at certain location, at certain point location, in, for example, I don't know, the Gulf Stream, and you need to have some other knowledge in order to know up until which to look in time and space to include your data variables. So do you get my question? Or?
Yeah, I mean, a little bit, this prediction paper here was trying to address this. So here there's a lot of data sets, and you don't know which are useful or which are potential causes. And that kind of did a dimension reduction in a supervised way so this is quite a simple approach here, by just taking your target quantity. So you pick out a target quantity, the stratospheric polar vortex, and then measure the lagged correlation of every grid point with the target variable. And then you cluster in this lagged correlation space to find regions that have a similar relation, positive or negative. And then you aggregate your variables across these nodes to identify, again, time series for these regions, and then do this next steps here. So this is maybe a little bit of an answer to your question. If you have a target quantity. If you don't, then the problem is kind of ill-defined. If you say, yeah, I give you this gridded data, figure out causality, then there's 1,000 ways to define nodes, and each one will give rise to a different causal graph.
Yeah, we'll look up into the reference.
But one thing is that for example, gridded data, if you take just the field of temperatures, then in my view, it doesn't make much sense to say whether a grid location at 50 latitude, 30 longitude causes the one at 30 latitude, 50 longitude or so, or the one next by, and then take all the other grid points as other graph nodes and then remove their effect, because that kind of puts a discrete causal graph across a spatially continuous physical system. And that is problematic. Like, I would rather do dimension reduction and define the quantities of interest beforehand and then use these in causal discovery, so that you are sure that the variables you consider are kind of autonomous physical quantities. So this is the assumption of this really first paragraph here, namely that the structural causal models represent independent mechanisms. Two grid locations are not independent mechanisms. They are strongly connected and redundant.
Yes. Thank you. Okay.
But it's a challenge, and you put the finger on the wound here. It's a challenge to define the variables. It's rather a technique for once you have the variables. But we're working on this. I'm strongly working on this, how to combine dimension reduction into causal discovery, and that's kind of at the forefront now. That's what my ERC grant is about.
Thank you. Thank you very much. Other questions?
I can have more questions if there are no more people. I have a question about structural causal models. If I'm not sure of understanding correctly, but basically in structural causal models, you can use different kinds of causality estimators. For example, you can adapt structural causal models to use Runge causalities as a measure of causality.
Yes. So causal inference, when you are given a graph, then the theory tells you which variables to put in your model. It doesn't tell you whether to use a linear or nonlinear function. That is also what you, as an expert, have to choose, or maybe you test around, of course. And here, for example, if everything is linear, then this multivariate linear regression would give you the right answer. But yeah, if it's a nonlinear relation of x on y, and also the relation to z is nonlinear, then you actually have physically, you have an effect of x on y that depends on the state of z. So you have a state dependency, and that would be then encoded in this function f of x and z. So you then have a multivariate function. Then only in the linear case you can reduce causal effects to one coefficient.
Okay, and about the estimators of causality relationships, such as Runge causality or nonlinear versions of Runge causality based on information theory. I'm pretty familiar with these methods, but with classical estimations. And I have observed that during the last years, there are the more and more estimations of causality, transfer entropy, or conditional mutual information that are based on artificial intelligence. I don't know if you are familiar with these estimations, and what's your opinion about that?
Yeah, I mean, so the nice thing is that it's kind of separate from the problem of causal discovery to some extent. Like when we talked about conditional independence, then this conditional independence can be implemented with linear assumptions, with Gaussian processes like additive, or fully non-parametric with conditional mutual information. And then you use such an independence test based on CMI in your causal discovery algorithm. You can also use a neural net. There's also neural network condition independence tests. Or if you stay in the Granger causality framework, which has this disadvantage of not being able to pick up instantaneous things, then you can fit a neural network model of y on the path of y and x, and then also only on y, and compare their residual errors. There's a lot of little issues to deal with, like the complexity of the models needs to stay the same so you don't get artifacts related to a different penalization term or so. But I'm not too much of an expert in this. But there's always different ways to do so. And yeah, some of them are listed in this perspective, for example.
Okay, thank you.
Okay, thank you, Jakob. I think we'll stop the webinar now. Thank you again for accepting to give your presentation. It was very, very interesting, very informative. And
Thanks.
for everybody else, including you, Jakob, you can meet us at the next webinar series. Thank you.
Yeah, thanks a lot for the invitation again. Bye-bye.
Bye-bye.